So here is an overview of inferential statistics with confidence intervals and the central limit theorem. And I'll also reflect back on the simulations we did with StatKey. So when we make a confidence interval, we're trying to make an estimate about a population mean. And so that would be, for example, our mu, the population mean, and we approximate it with our sample mean. And based on the sample mean, we generate, and the sample, we generate a margin of error. And with the margin of error, we can get an upper and a lower estimate so that we think with some confidence level, like 95%, that the actual mean lives inside here. Okay, so mu lives inside here as our best guess. The higher the confidence level, the wider the interval, and the bigger the margin of error. Unfortunately, the higher your confidence, that's good, but the bigger the margin of error, then people start to question your work if your margin of error is too large. So then sample size comes into play also. So there's a whole bunch of stuff working together to figure this out. So let's look at an example of this in just a sec. There are a couple of different kinds of confidence intervals we can make here. Often we use mu because we're talking about a mean. So if we're working with a mean, then there's one of two cases. Either we know sigma, which is the standard deviation of the population, or sigma is unknown, in which case we're going to approximate sigma with the sample standard deviation. If we know the population standard deviation, then we're going to use z-scores to create the interval. If we don't know, then we're going to use t-scores to calculate that, and they're done a little bit differently. The margin of error is calculated with a z-score, so the error bound on the mean would be the appropriate z-score, right? This z-score right here related to that lower 0.5% left over from the confidence level, times the known standard deviation of the population divided by the square root of the sample size. But often we don't know the standard deviation of the population. So then the error bound on the mean is calculated a little bit different. In that case, we have to find the appropriate t-score, which is very much like the z-score. And we use the sample standard deviation and still divide by the square root of n. So notice that they're similar. There is one other case that we would use a t-score instead of a z-score. And let's make that in red. So if sigma is unknown, or you have a sample size that is less than 30. So if you have a small sample, you would also jump to a t-score. Okay. So what that means is most of the time we don't know the population standard deviation, so we use a t, and sometimes we have a small sample, so we'd use a t. So it turns out with means and confidence intervals, we don't often end up using a z-score. So this is not often do we do this one right here. I'm going to do it today just for fun, and I'll compare it to that one. The other kind of test we can do, or a confidence interval, excuse me, is for a proportion. And with a proportion, we're going to use z-scores. And the mean for a proportion is going to be approximated by the sample proportion we call p prime, which is the x, the number of favorable outcomes, over the total number of outcomes. Okay, so this would be favorable over sample size. So maybe in a population, we're trying to see what percent of people got cancer. So X cancer would be favorable because that's what we're looking for. So favorable doesn't mean good, it just means whatever you're looking for. Could be the number of people adults who have children out of all the adults in a certain area. Okay, so the mean of a proportion is the proportion. The standard deviation of a proportion, sigma, we're usually going to approximate that with a sample standard deviation, and the sample standard deviation for a proportion is going to be p prime, so that x over n, times q prime, which is 1 minus p prime, divided by n, and then you have to take the square root of all of that. So that's the standard deviation for a proportion. And remember that q prime is always 1 minus p prime. Okay. So these are the majority of the formulas. The tricky thing is, how do you find the appropriate z-score? How do you find the appropriate t-score or z-score here? So when we're doing a confidence interval, we have to decide if we're doing a mean or a proportion. If we're doing a mean, we have to decide whether we use z-scores or t-scores. And we use t-scores if it's a small sample size or the standard deviation of the population is unknown, which is most of the time. But sometimes somebody just happens to give us, hey, here's the standard deviation of the population. And even if we know the standard deviation of the population, we still need a sample size greater than 30. So if it turns out, hey, we have the standard deviation of the population, but your sample size is only 10, then you'd have to use a t-score. All right, so let's try one. So I have some data here from statistics students in 2020. This is a little bit different than the data you all looked at a few weeks ago. These are the number of hours on average per day a student that took statistics from me this year watched. And so there's quite a wide range of numbers there in this column. If I go to the original data, I also collected some information on genders and quarter. But I have a count so far this year of 65 students took statistics with me and told me how much TV on average they thought they watched per week. The average was 3.152 hours per day. Sorry, hours per day, not hours per week. Standard deviation is an average spread of 2.157 hours per day. Minimum is, some people said none. Maximum, one person claimed 10 with a median of 3. And then I took a look at, within one standard deviation of the mean, what % of students were in there. So for this data set, we got over here, let's zoom in on that. 72% of students were within one standard deviation of the mean, 95 within 2 standard deviations, and 98 within 3, which roughly fits within the empirical rule. Here is the histogram of that. And so it's kind of normal, but we have a tail on the right. Here's a slightly different version of that. Same idea. Excuse the phone. So, I always like to do a histogram of my sample just to see what's going on. And I usually throw it in StatKey to do that too. So moving on. So I have a reasonably good sample size. And but I don't know the population standard deviation. And the other question is, what's the population here? Is the population BMCC students? Is it all community college students? And just for fun, I'm going to say this is a representative random sample of all community college students, which ain't true. This is a very convenient sample that could be very biased, but I don't really know because I'd have to do more study to figure that out. But we're just going to go with it. All right, so back to the confidence interval stuff. To make a confidence interval, you need a few things. You need to know your sample size. You need to know the mean. You need to know the standard deviation. Okay, so based on that, I drew up a little picture of it, and I used StatKey to run a simulation. And I'll go over how I made both of those in just a second. So I'm just going to recreate this stuff right here. So let's grab this column, start over, put it back in. All right, so first is my sample stats. And for my sample stats, I want to know the count, I want to know the mean, and I want to know the standard deviation, which we'll just call S because it's a sample. And that's pretty straightforward. Count, in this case, there's nothing else in that column, so I can select the whole column. Mean is average. And StatKey would give me all of this too if I just plugged it straight into StatKey. So if you don't want to use a spreadsheet, you don't have to necessarily. Whoa, didn't mean to do that. And the standard deviation. And I recommend using the standard deviation of a sample.s and grab the data. And if you're not sure about grabbing the whole column, then just start at the top and find the bottom. So that works too. All right, so that's the information I need. This data has 2 decimal places at most, I believe. Yep. So then I would round these to 3 decimal places. So we usually take the summary statistics one more decimal place than the data. All right, next thing I need to know is information about the sampling distribution. So sampling distribution. And you may forget what a sampling distribution, in this case, a sampling distribution is the distribution of means of samples of size 65 for the hours of TV per day. So let's go TV hours per day to be a little more specific. All right, and what do I need to know about the sampling distribution? I need to know what's the mean of the sampling distribution and what's the STD of the sampling distribution. The STD of a sampling distribution is also referred to as the standard error, which I often abbreviate SE. And what is standard error? It's just the standard deviation of the sampling distribution. That's it. Central limit theorem says that for a large enough sample, the mean of the sampling distribution is the mean of the population, and we're using our sample to approximate the population. So I can just say the mean of the sampling distribution is the mean of the sample. Standard deviation is a little bit trickier. Central limit theorem is a little more complicated there. Central limit theorem says that it's approximately the standard deviation. Let's see, where's my highlighter? Of the population divided by the square root of the sample size. Now I don't know that, so I'm over here in this section, so I'm going to say that the central limit theorem tells me that the sampling distribution has a spread that's about the sample standard deviation divided by the square root of the sample size. Oops, wrong one. Sorry about that. There we go. So equals the sample standard deviation divided by the SQRT of the sample size. All right, so notice that it's the sampling distribution is going to have a much narrower spread, and I'll demo that in StatKey in just a minute, but that's what the central limit theorem says. All right, once I have that information, then I can go make a confidence interval. Ooh, excuse me. That's better. All right, so for the confidence interval, I need to know what's the center of the confidence interval, so that means I need the mean again. And I need to know, let's see, what the standard error is, which I have above. I need the error bound on the mean otherwise. All right, error bound on the mean. Okay, so the center of the confidence interval is going to be the center of the sampling distribution, which is the center of my sample, according to the average. The error bound on the mean, I have to calculate the z-score. Oops, so I guess I'm a little ahead of myself. I need a confidence level. So let's go with the standard 95%. Then, once I have the 95%, I need to find the right z-score. So if we look back at my picture here, to find that z-score, I need to know what alpha over 2 is. So let's calculate that. So let's get alpha first. Alpha is always 1 minus the confidence level. And then alpha over 2, and we could grab the symbol alpha, but it's easier just to type the word alpha. So alpha over 2 would just be alpha over 2. Once we have that, and it doesn't matter whether it's a percent or a decimal, but let's be consistent, and we only need 1 decimal. Now we can find the appropriate z-score based on that. So there's 3 things you can do with z-scores essentially. You can take a data value and find its z-score. You can find a z-score based on a percentage, or you can take a percentage from a distribution and find a z-score. In this case, we have the percentage and we want to find the z-score, and that's kind of backwards. And so to do that, I need what's called the norm inverse formula. And there's a cheat sheet back in week 9 about this. So I want norm, and I like to use norm dot inverse. And norm dot inverse says what's your x value, and the x value in this case should be a percentage from a left tail. And the documentation isn't clear about that, but that's what it's got to be. It's got to be the left tail percentage. So that is my alpha over 2 above. And then it wants to know what's the mean For z-scores, the mean is always 0 and the standard deviation is 1. Now you might say, well, don't we have a mean and a standard deviation from the sampling distribution? The answer is yes, but that gives us a different answer, and I'll explain that one in a minute. So I'm just going to go with the straight z-score. All right, so this says the z-score is about negative 1.96-ish. So let's go to my sketch and add that. So in my sketch here, let's just edit this drawing. So I'm picking a confidence level of 95%. That leaves 5% for the tails to share, so that's 2.5% for this tail and 2.5% for that tail. Now, let's see, I'm running out of color here. Z-scores in the middle is z equals 0. So since I gave it the 2.5% over here, it's telling me the appropriate z-score here is negative 1.96-ish. Well, that means the z-score on this side, because of the symmetry of a normal distribution, must be z equals 1.96-ish, the positive version. And when we calculate the margin of error, we always use the positive version. So I need to tweak my spreadsheet to give me that positive version. So all I'm going to do is go back to this formula and sneak a negative sign in between the equals and the norm dis. So now it says equals negative norm inverse. And although I typed norm dot inverse, it picked norm inverse. And if I put the dot in there, it's not going to change the answer. They do the same thing. Okay, so I have that z-score. All right, so now I can find the margin of error. So according to the central limit theorem, the error bound on the mean is equal to the z-score, which I have here, times the standard deviation you're using, which would be the sample standard deviation, divided by the SQRT of the sample size up here. Now, just a reminder, this calculation I did right here, where I take the sample standard deviation and divide by the square root, that is the standard error there. So another way to find the error bound on the mean is just take the appropriate z-score times the standard error, if you've already calculated that. So I'm just going to double check that. Equals the appropriate z-score here times the standard error of the sampling distribution should give me the exact same number. Okay, so notice I match the exact same number. Now, once I have that margin of error, right, so that's what I just calculated here, margin of error, I can find the lower and upper values for my interval, lower and upper. And the lower is simply start in the middle at the mean and subtract the margin of error. And the upper is simply start at the middle of the mean and add the margin of error. All right, so that's the spreadsheet method. It's a good amount of work. And this is according to the central limit theorem. Now, I kind of fudged the central limit theorem. Remember that flow chart I made back here? The flow chart said I should use z-scores over here. Let's get that highlighter back. I should use z-scores if I know the standard deviation of the population, which is what I just did. But oops, I really don't know sigma. I should have used a t-score. So we're going to do the calculation with a t-score for a comparison now, just for fun, because that's really the more appropriate way to do it. So if this were a homework problem, and I just said find the margin of error and confidence interval for this data set here, and that's all I gave you, you should use a t-score, not a z-score. Okay? So I shouldn't have done this right here. So I'm going to highlight that in red. Okay, so what I should have done for that is a t. So let's redo it. Confidence with t. We still need to know the mean. We still need the confidence level. So really I can just copy this stuff right here. And let's change the coloring. All right. Now instead of finding a z-score, I want a t-score. So where I used over here to get the z-score, I used the norm inverse formula. In this case, I'm going to use the t inverse formula. And the t inverse formula is slightly easier to use. So t.inv. It wants to know what's your tail probability. Okay, I got that above here, comma, and it wants to know the degrees of freedom, which is always one less than the sample size. So all I do is go click on the sample size and -1, and that's what's called degrees of freedom. And there is my t-score. Notice it is a little farther from 0, 1.9977 versus 1.9599. I really don't want that negative there, so I'm just going to sneak in after the equals and change the sign by putting a negative in there. Otherwise, it works pretty much the same. Let's see, these guys don't quite line up. Let's shift you down just a little. Better. All right, so for the margin of error, error bound on the mean, pretty similar to before. I'm going to take my t-score, and I'm going to multiply that by the standard error, which again is the sample standard deviation in this case divided by the sample size. And notice I have a slightly bigger margin of error, 0.5344 versus 0.5243. Okay, so slightly larger. T-score usually looks a little wider to try and find that population mean, to take into account that you don't actually know the standard deviation of the population. So we just spread our net out a little wider. The lower and upper bounds are exactly the same once I know the margin of error. It's just simply the mean, oops, which I forgot to get. So let's go over here and get it, minus the margin of error, and then the mean plus the margin of error. So we have a slightly wider interval here. Okay, so just a little bit wider. Let's see, 2.2618 versus 2.628. Okay, so I'm a little lower on the left, and I'm a little higher on the right. 3.687 versus 3.677. And this is the appropriate way to do it because I didn't know the population standard deviation. So I'm just going to make a note. Population STD unknown. All right, let's compare what StatKey says about this, and I'll explain what StatKey does when you use a simulation. So the method I just used is based on the work we did last week about the central limit theorem. And 3 weeks ago, we used simulations. So StatKey, I want to do a confidence interval for a mean, and then I edit and delete all of their data. So highlight and delete, and then paste in, does my data have a header row with a title? The answer is yes, it does. So I leave this data has header row checked, but I don't have a first column identifying each of these numbers. Like that would be, this is Gary's number, and that's Beth's number, and that's Julia's number, and so on. All right, click OK. So this is a dot plot of my data. And if you look at that right there and compare back to my spreadsheet, remember I did a histogram. It doesn't look too different from my histogram. It's got that right skew there. Same right skew there. Then I just want to generate thousands of samples. Remember the recommendation was at least 6,000, so I'm going to go with 7. And then I want to do a two-tail 95%. And here they say, okay, you should have 2.658 on the left. What did we have? So let's make a comparison. My new one, here we go. Let's delete that. And put above here StatKey. So StatKey says the lower bound is 2.658, 2.658, and the upper is 3.685. Interesting. 3.685. So this, notice this lower bound is a little higher than that one, and the upper bound is a little higher than that one. The upper bound is closer from StatKey to the t-score on the upper, but farther away in StatKey from the t-score there. So let's highlight StatKey. It's a different technique. So this was based on a simulation. Let me remind you about what that simulation is. So StatKey takes all of the numbers I gave it, and makes a deck of cards out of it. And then what it does is it shuffles the deck and it draws 65 cards from the deck, but only one at a time, putting the cards back in. So it draws a card, says, oh, 3.5, puts the card back in, shuffles, draws another till it has 65, and it builds a new sample. So some of these numbers, like this 8 here, these 8s here could occur more times than they originally did because we're shuffling with replacement. And then it just makes a whole bunch of new samples. So I have 7,000 samples of size 65, and there's a whole bunch of dots here. And if I point to a dot, it changes the sample over here. And so sometimes the dots had more on the lower end of watching TV per day. Sometimes it's more on the upper end, but mostly they ended up in the middle. So it's kind of interesting that this random shuffling of cards, when we draw a picture of the means of each of those 65 draws 7,000 times, ends up having this nice symmetric bell-shaped curve. Yeah, there's a little jaggedness to it, but if my sample size was larger than 65 and I did more than 7,000 samples, it would smooth out. And the bigger n is, the smoother this will look when you run a simulation. And if I reset this and run it again, I'll get slightly different numbers, but they'll be in the ballpark of what I just had. Let's go 8,000 this time just for fun. So 2.637, a little lower than last time, and 3.681, a little lower than last time I ran the simulation. Notice they give a standard error up here, 0.267. Compare that to the standard error over here, 0.267-ish, 2.68, or 0.268. So the standard error, how do they calculate that? Well, they don't use the formula that I did here. So they didn't take the sample standard deviation divided by the square root of 65. Instead, what they did is they took every one of these 8,000 means and applied the standard deviation formula, which is a bit complicated. You could look back in chapter 2 if you want to see what that looks like. So they found the standard deviation of these 8,000 means, and it turns out to be almost exactly the same as what the central limit theorem says it should have been. Okay, and we've been using the central limit theorem for a long time because we didn't have computers powerful enough, say 20 years ago, 30 years ago, 50 years ago, to do what I'm doing on my laptop right now, which is nuts. So simulations have changed statistics dramatically, and they make a lot of stuff more accessible than it used to be. We can solve problems that we couldn't have with theoretical formulas. So this is an experiment coming up with a confidence interval, which matches the theory of what the central limit theorem says, and this is actually the correct approach for this situation using the t-score there. All right, so this is just a summary of how to use a spreadsheet with the central limit theorem for a confidence interval for a mean. This over here would be if we had known the population standard deviation, and this over here is if I don't know the population standard deviation. Sometimes in the problems you're given, you have the data. Sometimes you don't. You just get a summary. If you're just given a summary, you cannot run a simulation because the simulation requires that you have the actual data. Okay, so the simulation for a mean only works if you have the actual data. A proportion's different. You don't need the original data. All you need is the summary. You could do a simulation also. One more thing I'll show you, then I'll shut up for this one. I could use the theoretical distribution normal or t. Now the normal is a little more powerful. The t is a little harder to use in some sense because all it does is make t-scores. So I would enter my degrees of freedom, 64, and then I would say I want a two-tail 95% confidence interval, and it says, okay, your t-score is 1.998, which the spreadsheet gave us over here by using that t-inverse formula. So you may decide, I don't really like the spreadsheet very much. So StatKey can find a t score for you if you need it based on a tail probability. So that's there for you if you want it. Other interesting thing is if we happen to know the standard deviation of the population, so let's just make believe we do. So let's say this is actually sigma here, not s. Then what I could do is on a handheld calculator, I could calculate the standard error, which remember the standard error is the standard deviation divided by the square root of the sample size. And so let's round that down a little bit. I'm going to take that to, let's say, 4 decimal places there. So 2675. So if I plug in the mean and standard deviation of the sampling distribution into that theoretical normal, 2675, let's try it. Edit parameters, mean was 3.152 and the standard deviation was 0.2675, is that right? 2675, yep, to 4 decimal places, hit enter. And then if I say, hey, yo, two-tail, what it will calculate for me are the actual boundaries of my confidence interval. So the theoretical normal can do a confidence interval if you know the standard error. Okay. It doesn't work for t-scores. T-scores are just a bit more work. And I don't have an easy way around that. So that's where we're at. Hope you found this enlightening. Stay in touch, do good math, study hard. Bye-bye.